The next thing we're going to look at is the assignment fit. So uh, before we looked at the geometry, we also looked at the demand configuration. So we looked at all the inputs for the demand. But now what we want to look for is all of the outputs. So the way Vissim works is we have vehicle inputs and we have static routes that dictate flow rates coming into the network and turn movements and things like that. And from an input perspective, those all should be assigned based on the counts that we may have. However, now what we want to look at is whether or not the input values that we give are giving the correct output values. So we can control for things like queuing and latent demand. So we want to see if the actual simulated turns are matching the inputted values and things like that. Okay, so based on field data, we have three different aspects that we can look at. We can look at turn counts using the node results. We can look at how many inbound and outbound counts there are for each location and of the various turning movements. These are done using the node evaluation tool, which we saw was drawn around different intersections. Another one we could look at are link flows. So each link, like we saw before with the speeds, is reporting a volume over the time interval, a flow rate per lane over the time interval. And so we can look at the average level link flows um, for different time intervals or across the whole simulation and compare that to our field data. And then we can look at our data collection points. Data collection points are specific points in the network that act like gates, so that when vehicles traverse that gate, they are recorded. And they record things like speed, acceleration, occupancy, and their counts. These are supposed to imitate things like induction loop counters or pneumatic tube counts or video counts. Basically, data collection points kind of act like uh, stand-ins for counting stations that you might have out in the actual network. And so you'd be, again, comparing data collection point results to speed data that you might have at a specific location or uh, axle counts at a specific location, things like that. So these are the three main areas of investigation that we're going to take a look at when it comes to looking at how well our assignment is actually fitting to the network. Starting with things with node evaluations, what we're going to do is we're going to take a look at the intersections themselves, and we're going to make sure that the turn counts and everything are appropriately matching what our field data specifies. Now, in this case, there are two ways that we can go about this. We could go from a visual perspective, and so Vissim has this graphic that I'm showing here on the screen. Turn value visualization tool where you can see the inbound and outbound counts at an intersection level. We also have a list view of this same data where it will show each movement through a node um, and record things like delay and volume and stuff like that. But for assignment fit specifically from a review perspective, validating that the model has been appropriately built out. We're just going to be looking at volume, not necessarily delay per se, but that is also a result. One thing I do want to note about our node results is that the nodes themselves record when a vehicle crosses an edge of the node. So a through movement in this situation is considered a vehicle that crosses this edge and then exits out this edge. And Vissim is able to differentiate between different movements depending on which edge they have entered and exited. So for example, they may have entered this edge, done whatever, and then exited out this edge. So depending on how the node is built out and what is included in the node, there can be a lot of different actions happening. So for example, if you have a roundabout, maybe they go around once and then they come out. that would still be indicated as a right turn movement because they entered along this edge of the node and then exited along that edge of the node. So that's a clear distinction about the process of how Vissim calculates counting vehicles that have performed that movement. One other thing to note about uh, the node evaluation is that it only records vehicles in the count perspective that have completed the movement. So for example, let's say that out in the field, you get a 15-minute count that says 300 vehicles should have turned right at that over that 15 minutes. So you put in a vehicle input of 300, you put in a static route that says 300 vehicles turn right, and then you run the simulation. Um, Now, there could be various reasons why your output result doesn't equal 300. It could be because the signal timing wasn't adequate enough and those vehicles couldn't get through. It could be something like the input location was really far away, like maybe the approach, for example, was 2 or 3 miles upstream of the intersection, right? So typically what will happen is out in the field, the modeler will have collected data at the actual turning movement and then build out the network back, say, a mile upstream and then put a vehicle input over there. And so there's this, this run up distance between the input location where you're actually feeding the vehicles into the network and the vehicles that have actually completed the turning movement. So this is another important reason as to why you would need a warm up period, because if you started the simulation and immediately started collecting your node evaluation, if there's any sort of distance between the input location and the turns, those turns are going to be undercounted because there's going to be some number of vehicles that have to drive up to that location. Whereas if you start with a warm-up period, vehicles are already at the intersection when you start counting the data, and then they start moving. Now, if you have significant distances, and I'm talking, if you're doing a freeway model, um, and maybe there's like 5 or 6 miles of run up before the first exit, and then there's a node there, and the only place where vehicle input is 5 miles upstream. That's 5 minutes of delay between the input count value and the turn count value, right? So if all you've done is made turn counts, collected turn counts at the intersection, and then put those turn counts in a vehicle input 5 miles away, let's say that your turn count jumps from 300 up to 500 in the next 15-minute interval. Well, that's immediately going to happen at the vehicle input, but there's going to be a 5-minute delay between when that increased flow rate of vehicles gets to the intersection. So that's something to consider as well. If your vehicle inputs are significantly far away, you're going to, just because your turn counts maybe aren't coming in correctly, that might just be an issue with you need to offset when the vehicle inputs happen versus when the counts are happening. I do this all the time from a pedestrian modeling perspective. Um, the anecdote I like to use is I did a transit center model uh, where all we had was ridership counts. Uh, so what we had to do was we had to back calculate how long does it take a person to get out of their car and walk all the way to the platform and then get on the train that happens at 6:05 in the morning. When the train gets there, 300 people board. Well, we had to back calculate, and our vehicle inputs were actually offset by about 8 minutes because that was the average amount of time it took people to get from the parking lot to the platform. So it was, through all the ticketing and coffee and all that stuff. So that might be something that you consider retroactively going back and talking with your modelers about if there is significant gaps in travel time or something like that between your counts and your vehicle input points, just because there is opportunity for that to happen if those distances are too large. Okay, so from the node results, we're going to be looking at the volume of vehicles that have completed the turning movement. And so it's going to count each vehicle that completes that movement. And so if the counts are too low, you might also pair this together with something like Q data or link count data to determine are those missing vehicles, are they stuck in a queue somewhere? Um, Unlike something like HCM analysis, at if you're using Vistro or if you're using a travel and man modeling tool where the intersections are analyzed as independent objects, um, upstream calibration can affect downstream results. I get this question all the time in support. Hey, we did an arterial analysis using HCM, and it was level of service uh, C at one intersection, and then the next downstream it was level of service uh, C at the next intersection. But when we come into Vissim, it's we have a certain level of delay that matches at intersection one, but the next downstream intersection um, is performing better than what we saw in HCM. And that's because, maybe that upstream intersection was limiting the throughput. So the actual vehicles that were arriving at the downstream intersection were more limited than what you saw, or something, or maybe vice versa happens, where the downstream intersection is level service F, and those spillback queues weren't accounted for at the HCM level, whereas that would be captured in VSIM. So if your counts are not fitting correctly, you're going to want to zoom out a little bit and look at the broader perspective of, do we have some sort of bottleneck upstream that is limiting the counts, making them too low? Or if the counts are too high, um, is there some sort of, or maybe the volumes are too low because there's a downstream bottleneck that is causing a queue to back up, and the vehicles aren't pumping through enough, right? And so those are some kind of considerations that you're going to want to make when looking around at an intersection, as opposed to just being zoomed in on it. You might have to pull back a little bit and see what the greater context is. Okay. With the link results, what we're going to be looking for mainly on this one is things like lane utilization, um, and flow rates through a facility, right? So the intersection analysis results are going to give us turn count data. These are going to give us data where you're not having a node, so maybe a merge or weave area, as well as lane utilization between, even on arterials, where is heavy utilization happening? Is everyone supposed to be stacked up in the right lane? Are they all supposed to be stacked up in the left lane, or maybe in the center lane? So you're going to be looking for these trends, and that's going to be displayed on a heat map, where we can see, darker colors mean higher volumes, and so you can kind of see those relative shares of volumes on the links themselves. And then finally, we're going to be looking at data collection points. Again, typically data collection points are going to be mapped to real world collection sites in the network. So if you have a collection site in the network, typically there's going to be a data collection point in Vissim right there, because data collection points are one of the easiest ways to validate a model, right? So you've gone out and you got a ramp count. So you're going to drop a data collection point in right there, and you're going to see if the right number of vehicles at the appropriate times are pumping through at that location, right? And so data collection points are going to be pretty ubiquitous throughout most models. What I would highly recommend is that you push your modelers to name your data collection points, or at least give them reasonable IDs, so that way you can somehow map them to different count locations, because a lot of times they just get left as empty, um, and they're blank, and so you kind of have to do some detective work as to figuring out, okay, which data collection points are referring to each count location. So as long as they're being named and grouped together appropriately, it can make your job on the back end with review work a lot easier. We're also going to be looking at making sure that we have full lane utilization. Now, this is an example, again, of the node display, but instead of showing the turn counts, we're showing the queuing. And in particular, what you want to look at is whether or not the turn pockets are being utilized, because they can get blocked by queues in other lanes. So on the left side here, we see the cues reported for each particular movement. We have the right turn movement cue, we have the through movement cue, we have the dual left cue. We also see for this outbound movement, we see a cue spilling back into the intersection. So that's also important to notice too, is that we do have some cueing spilling back into the intersection, and that's resulting in this right lane being completely filled up, right? And so we have this single right lane that's being full, and so it's filling up, and you see that it's going all the way back to the start of the turn pocket. So this right lane is being fully utilized. And if we look at the left lane queue is going to be underreported. And so if you're just looking at the queue results in like a list format, it's going to say your queue is 0 or what have you, because you're not going to be able to see the queue forming. And that's because this through movement is blocking that queue altogether. And so nobody's able, all these left turn vehicles are probably stuck back here somewhere in this larger queue. So that's something to consider. In this particular scenario, what would happen is your through movement queue would be reported as really long, and your left turn queue would be reported as really short, compared to maybe what your field data is saying. And this might be an issue with, you need to prevent blocking the intersection. Maybe this queue is really long because we see these cars are queued up into this intersection. And so maybe you need to throw down some priority rules or something like that, so that the cars don't turn left and just sit in the middle of the intersection, or go through and sit in the middle of the intersection, so that some of these through movements can flush out or something like that. So that might be an issue with calibration or gap acceptance or behaviors that you might want to look into further to make sure that the adjacent lanes aren't being blocked and things like that. Another thing that we're going to want to verify are whether or not vehicles are turning at appropriate locations, or the movement through intersections is appropriate. We already looked at this at a freeway level, but we're also going to look at this at an arterial level, making sure that vehicles are merging and weaving at appropriate locations. Here we have a link level heat map showing the speed of the vehicles going through a roundabout. And in this case, what we're seeing is that as vehicles are entering the roundabout, we're seeing the circulating vehicles in the roundabout coming to, really low speeds. Everywhere else, it seems, they're going about 15, 20 miles per hour, except at this one location where they're going 10 miles per hour. And just from a quick glance, what it looks like in this perspective, for example, is that these vehicles that are coming here, I'm guessing a lot of them are trying to go southbound. But what's happening is we see that this movement has 2 lanes, and that these vehicles are merging into the inner lane and then needing to make a lane change and then make a turning movement, right? That can be an issue because in a roundabout, you're not supposed to be making lane changes, and these guys are supposed to yield to them, but also these vehicles before entering the roundabout are supposed to yield to circulating vehicles. So because of the way this roundabout is set up, it's properly making the yield behavior on the inner lane, but on the outer lane, these vehicles have the right of way, essentially, because these vehicles have to make a lane change across their traffic. And so what that's causing is vehicles to come to a stop in the roundabout, waiting for a gap as other vehicles are just kind of driving past them. And that can cause different types of behavior issues in that particular case. And so that's one example of where you're going to be looking for inappropriate lane change behaviors, in addition to the ones we already looked at where vehicles are making last minute dives into a queue or something like that. Um, so again, we're going to verify that there are no vehicles at inappropriate turning locations or anything like that. Um, Also, I'm going to give, when we jump into this, I'm going to be loading up an animation. Again, I didn't upload the animation to the example files because it was a 10 gigabyte file, roughly. It's 9 point something. And so that's just way too big to ask all of you to download. But if you want to have the animation, you can always rerun the animation. Um, so what we're going to do is we're going to start by looking at the input-output validation of the nodes um, and the links. So what we have here is we have the links being displayed with average volumes on the links as a heat map. But if we zoom in, we can also see that the nodes are being displayed using our uh, show turn value visualization tool. So if we zoom in on a node, we can see the turn value visualization at a particular node, and it's reporting, in this case, all the different turning movements, as well as the approach volumes and the outbound volumes of the node from a particular time interval. I believe this one is average across the board, but we could also pick out different time intervals. So by default, this graphic overlay that we've created for you just shows the average across the whole simulation. But you don't have to just look at the average. Maybe you want to look at the peak hour or a specific time interval. What you can do is on these graphic parameter settings, if you come into the graphic parameters, for the links, for these link volumes here, there's a, if we come down, we see it says volume average all. What that is referencing is we ran 6 simulations to collect data on the network. Or in this case, we ran 5 simulations to collect data on the network. And then within each one of those simulations, we have a 15-minute link interval or evaluation interval, meaning every 15 minutes of time, we are collecting data and aggregating it together to give us speed, volume, density results. And so what we're actually displaying is across all, the first average is referring to the simulation that we are displaying. In this case, it's taking all 5 of these simulations and averaging them together. And then the next average is the time interval. And so it's taking all the time intervals. In this case, we have a 3-hour simulation broken up into 15-minute intervals. So we should have 12 different time intervals. It's taking the average across all those time intervals. And so we're getting a nice average value that we're displaying. But if we want to pick out a specific time interval, we'll open up our graphic parameters here, and we can go to a color scheme configuration where it says volume, average all. And if you hover over it, you'll see that we have these little 3 dots. And if you click on those 3 dots, it'll open up our color scheme editor. And you can see that the color scheme here is already defined as in the legend. And then the attribute that it is based on is volume, average all. But if we click this pencil, we could pick a different simulation, or we could pick a different time interval. So in this case, we can find the maximum values, we can find the minimum values, we could report a specific simulation, simulation 1, simulation 2, simulation 3. I don't like to report a specific simulation because each simulation is going to have a bias towards that particular random seed. So I always like to use the average simulation. Because again, that's like taking, going out into the field and counting 5 days of the week and then saying Wednesday is representative of all days of the year, right? As opposed to going out and for 2 weeks collecting turn count data and saying, okay, we're going to average all that turn count data together, and that's going to give us our average that's representative for the year. So this first value, I always like to pick average, but if you want to pick a specific time interval, that's this second, you see average X, and here's that specific time interval. So this is that first 15 minutes, here's that second 15 minutes, here's that third 15 minutes, and so on and so forth. So we have 3 hours of simulation in the PM spectrum. I'm guessing this is probably somewhere between like 4 and 7, or maybe 3 and 6, or something like that. So our peak hour is going to be somewhere about an hour in. So I might do this 4,500 to 5,400, or maybe 5,400 to 6,300. Because an hour is 3,600 seconds, but remember we have a half an hour warm-up period. So this is after an hour of simulation. So this is that first 15-minute interval of the second hour. So I can click this one, or you can just count down. Here's 1, 2, 3, 4. That's the first hour. And then here's hour number 2, interval number 1. So I can pick that guy and click OK and click OK, and it will report the flow rate on the links based on that specific time interval. We can do the same thing on the node evaluation. Right now it's reporting average across the board. So I can click the graphic parameters, and where it says show turn value visualization, I click the 3 dots right here. And again, it says vehicles average, average all. I can find average, and in this case, I want to do that 5,400 to 3,600 again. All vehicles. Click OK. And now it will report that specific time interval's turn counts. So that will allow you to pick out specific time intervals that you want to visualize, as opposed to just an aggregate across the 3 hours. So you can kind of create this information. If you want to look at this in a list format, you can always come up to Evaluation, Result Lists, and go to Node Results. So if you wanted to look at all your time intervals side by side, instead of just visualizing one time interval at a time, you can click Node Results. And here, there's a lot of lists. We have 33,000 rows. But what this is each row is showing a particular movement of a particular time interval for a specific simulation run. So in this case, we have 5 simulation runs. We have, I don't know how many nodes do we have. We have 31 nodes. So 5 simulations times 31 nodes. And then, those, each node has somewhere between 6 and 13 different movements potentially. So in this case, we can sort by excluding specific simulations. So maybe we just pick out the average. So that cuts it down to 3,600. And then maybe we pick a specific time interval, right? Let's pick that same time interval at 5,400 to 3,600. So now we're just looking at 3,600 results. And then so here we see under the movement, we see each node number in the list, and then the queue results, the counts, level of service, vehicle delay, number of stops, emissions, things like that. And again, it's reporting for all vehicles versus cars versus just trucks. And so we can get these values side by side. And you can copy this out to Excel and create charts, things like that. Or what we could do is we could filter by specific movements. So let's say we want intersection number 1 for all time intervals, right? So here's all 12 time intervals for intersection number 1, and this is just showing the intersection total, right? So all the vehicles that went through this intersection across all time intervals, you can see all these values side by side. If you want, you can highlight these and right click, and then Vissim has an ability to create a chart for the selected attributes. So you can look at a chart that over time shows you the volume that has gone through intersection number 1, right? If we highlight all three columns and right click, we could say create chart for selected attributes, and it will show the different vehicles for each movement, right? And so we can look at that. Or maybe instead of limiting by movement, we turn that off. I want to say it contains, and we can pick out just the intersection number 1 movements like this. And so maybe we want to just report all the time intervals for all the vehicles for each movement. And so you can create a chart for the selected attributes that way, and it'll show each movement as different time intervals. So you can see as the vehicles make a particular movement, what is that what is that flow pattern looking like throughout the course of the simulation? And then at the end, it's the intersection total, right? So there are other ways that you can also visualize the data just um, beyond just the turn value visualization. But for validation purposes, what you're doing is you're trying to compare it to existing turn counts or future counts and things like that to try and get that data out. Finally, after we've done the links and the nodes, the last one we want to look at is the data collection points. So here we have a bunch of data collection points, and what Vissim actually does is it groups together those data collection points into things called data collection measurements. So here we have 352, 351, 352, 355, and 356. And these are all grouped together into a specific data collection uh, group that we call a data collection measurement, numbered 351. So now we can go evaluation result list and look for data collection results. And I want to find specifically number 351 right here. And so at this location, these 4 data collection points are reporting, we could again do a specific simulation. And so we have 12 time intervals. They're reporting the average acceleration across those time intervals, the acceleration for cars versus the acceleration for trucks versus the number of total vehicles, the number of cars, the number of trucks, the number of passengers, any queue delay that they've accumulated up to that point. If I scroll over, we could look at their speeds. We have 2 different speeds. We have an arithmetic speed and a harmonic speed. The harmonic speed is supposed to imitate a space mean speed. Um, so in the field, there are 2 ways to collect speed. We have time mean speed, so you could put down a tube count or an induction loop counter and count the vehicle and get their spot speed at that location as they cross that. But that doesn't account for anything like congestion or anything like that. They could just happen to be in a shock wave and be slow during that point or be fast during that point. Another way to collect speed data is over the course of a distance. I did a study with FHWA where they used video drone data to collect speeds over the course of 100 yards. And so instead of a single point, they were measuring the speed of a vehicle and they collected the average speed of the vehicle over 100 yards. And that's what we call space mean speed, where they're measuring how much speed what was the average speed across that interval. And that's kind of what the harmonic speed is supposed to represent, is that space mean speed kind of output. Um, so it gives you a little bit more of a smoothed out speed. So it'll look a little bit different than the average speed. So those are the 3 ways that you can go through looking at data. Again, we're looking at the evaluation results. We have node results where we can get movement-based data. We have data collection results. We have data collection results where we can get vehicles spot point data. And then we have link flow results where you can kind of get general trends and things like that. I One last thing about the link data is the link heat maps are really good for spotting out bottlenecks that maybe you weren't aware of or are hidden, because all of a sudden there'll be a large drop off in color. Maybe there's a lane drop or something like that, or a weird congestion issue, where you'll see all of a sudden the color go from a dark blue to a really light blue or something like that. And that'll be a good indicator of where the congestion is happening that might not necessarily be where you expect it to be. After we've checked and validated our different counts and movements throughout the network, We can then go into our turn-based visualization. This is that queue visualization that we were looking at earlier. Now, queue results are only going to show up around the nodes. But one key thing about the node results is that the queues report back to the next node's um, traffic control device. So if we look at this this node here, this northbound node, you see that we have this long queue spilling back through a few different intersections. Um, so it looks like this northbound movement is fairly congested for a good chunk of the way, all the way up to here. Maybe a left turn or something like that. So there's a long, I guess this queue stops short, so it's not spilling back there. But we have this left turn here that's filling up this entire turn pocket. And then that's spilling back to this intersection and then cutting off right here. That doesn't mean that the actual effective queue for this turn ends there. That just means that that's where the reported queue stops. And that's because there's a gap here where vehicles aren't allowed to traverse, and then it goes to the next traffic control device, which is right here, and then the next node's queue picks up at the traffic control device and spills back to the next intersection. And in this case, there's nothing protecting this intersection from getting blocked, so the queue spills all the way back to here. And then it keeps spilling back, and there's nothing in this intersection protecting it from getting blocked, so the queue spills back, and then there is a traffic control device here. So you see queues spilling back quite significantly um, through multiple intersections. Now, how this is going to manifest in the data output is that this queue right here is only going to report as about 395 feet, despite the fact that this left turn could potentially be causing a queue that goes all the way back to this location here, right? Because there's a spillback queue happening. So if I were to take my measuring tool and measure back from here all the way to here, that could be a 1,300 foot long queue that's caused by this single left turn. Not everybody's turning left, but there's enough people turning left that they're blocking the through movement, and then those through movement plus left turners are blocking everybody else down or upstream. So that's something to consider with the queue result data. Is it can be kind of misleading in the sense that it stops reporting when the next queue starts. So in this case, this intersection's northbound left is reporting roughly 400 feet. This intersection's through movement is only reporting 100 feet. And then the next intersection, or 110 feet, or sorry, 369 feet. And then the next intersection is reporting 225 feet. But that's not taking into account these gaps between the queue and then the next queue down, right? So there could be longer queues that are affected. Whereas if we look at this eastbound movement or this westbound movement here, you see how since we don't, even though there are intersections here, we don't have a node box, so the queue doesn't get cut off. So this right turn queue is going to effectively report at, almost 2,000 feet there and 2,000 feet there, and all the way back to the start of the link over here, right? So those are some things to consider. If you have closely spaced intersections, the queue results could be a little bit funky, and that's where queue counters are going to be really effective. I don't think this model has any queue counters in it. But what queue counters do is they allow you to ignore the node level queues. So if I were to drop a queue counter on this left, it would report the true queue as it spills back through the intersections. And it would basically report where the longest point was. So what it would do is it would look at this snapshot. Sorry, I'm trying to get the zoomed out far enough so we can see effectively. So if I start my measuring stick on this left turn, it would report this. It would look at this queue and it would say, okay, here's one potential queue. Here's another potential queue, or up to 1,100 feet. Here's another one up to 1,300 feet. But there's actually also this one that goes out to 3,000. This one out to like 3,000, and then we have this one that's out to 3,000. So if we were to drop a queue counter there, it would report a queue of 3,000 feet because it would ignore the upstream signals and say, okay, there was not a steady break in the queue anywhere going all the way back 3,000 feet. So that's something to look at when you are observing these queues. Making sure, for example, this right turn is going to report a queue of 65 feet, but this left turn is blocking that turn pocket, right? So you're going to want to look for that kind of thing, because this might be underreporting what you saw in the field, and this might be a calibration issue or a signal timing issue or something like that that's causing these long queues. Maybe this is a protected and a permissive left, but they forgot the permissive part. And so the throughput of this left turn is really low, or the aggressiveness of the conflict areas managing that left turn is not strong enough. And so vehicles are waiting when they should otherwise be going, thus diminishing the capacity of this left turn. And so those can all point to calibration issues. If this doesn't match the field conditions. So that's the kind of stuff you're going to be looking for with these lane utilizations, right? Looking for how are your queues reporting correctly, or are the lane utilization and turn pocket utilizations being fully utilized, or are they being blocked? So those are what you're going to want to look for there. Okay. And then finally, looking at the inappropriate turning behavior. Again, we already kind of looked at this on the freeway movements, but from an arterial perspective, if we look at the color scheme, this is the speed average, right? This is reporting zero speed, or when it says undefined, what these gray links are saying is that nobody utilized these links. So that's really curious that nobody's turning left there. Is that a routing issue? Is that because the queue was blocked? Right? Again, we can go through and we can pick out specific time intervals, and we can try and see if this is a specific time interval. But since this reporting is undefined, I would assume that means that there's zero. So let's start at the first time interval, though. And the first time interval is 0. So it looks like this queue is being blocking quite early on, even into the warm-up period. So if we go back one real quick and look at our turn bay utilization, I'm going to look at my node results, queue length. Let's take a look at our average for that first time interval. So what does our average queue look like in that first time interval? So what this is saying is in that first 15 minutes of evaluation, the queue is already backed up to here, which is telling us something very important, that by the time the warm-up period has ended, there's already gridlock on the network. So from this point on, nobody is going to be turning left, right? And so that could be a huge indicator by going into this, checking the inappropriate turn behavior. Anywhere where you see gray should immediately stand out to you and say, why is nobody utilizing this movement? Is it because there's no volume there? Is it because there's too much volume blocking other movements? We're looking at an average time interval, but we could always pick out a specific time interval. And if we pick out, for example, the first time interval, and we're seeing, orange, or something like that here. These are red because it's stop controlled, but otherwise they're moving pretty okay. So you're going to want to look for areas where vehicles are going slow when they otherwise shouldn't be, or maybe they're down in the pink. If the average speed for the entire interval is less than 10 miles an hour, that tells you that there's probably something up there. And you'll want to investigate that further, looking at queuing results or checking the volume inputs or something like that, because that's telling you that if the speed is really low in those locations, where's that roundabout right here, right? If the speed is really low in this location, that's telling you that that's some sort of behavioral issue, right? And in particular, this roundabout, you'd expect this connector to be something like this, where it kind of acts like a turbo roundabout and it pushes vehicles to the outer lane. Otherwise, what's going to happen is vehicles are going to be forced to make a lane change in a very short amount of time, and there's not enough room there to really make a lane change, right? So this might be a configuration issue where otherwise, if we look at it from just the default view, it looks fine, right? At first glance, you're not going to notice anything is wrong with it until you start getting into these result data. And now you're looking at these uh, inappropriate turn values and you're saying, okay, there's something weird going on here. We need to investigate what's going on. This is where I'm going to also open up an animation. And again, what I've done is we recorded the animation. So if you go into the presentation menu and go down to animation recordings, there's an animation recording set for the peak hour, right? So for that middle hour time, where all this is doing is recording the trajectories of the vehicles. So we don't have to hit play on the simulation and rerun the simulation all over again. All we're going to do is play back what happened during that value. The only problem is that file was really large, so I couldn't upload it for you to download. So if we look here, this file was 9.2 gigabytes. And the reason it's so big is because it's recording every vehicle, every tenth of a second, where they are and how fast they're going. But what this allows us to do, if you have this animation recording, is if you go to presentation, you see how we have this purple play button. This allows us to run that animation. You can also just right click and say animation and give us this purple play button right here. So I can hit play, find my animation file and hit open. And what this will do is this should run that animation. So now I can see the cars moving around in 2D and in 3D mode. But it's not re-simulating the network. It's just playing back what happened in that network. So we can see the bus, making a stop. But what I want to do is I'm going to pause real quick. I want to find that roundabout real quick. So I'm going to pause it. And I want to find our roundabout. And I want to see that behavior. So where was it in 2D? I forget. Okay, it's kind of near the DDI a bit. Okay, so for near the DDI, I think I'm too far up. I think I want to go down here. Yep. So what I'm going to do is I'm going to just observe the behavior that's happening at this roundabout. And I want to see why vehicles, sorry, my computer's a little laggy with the animation running. But what I want to do is I just want to see what's happening with these vehicles. So we see this blue box coming at us. This is that error that we saw earlier that was vehicles, models that couldn't be loaded. This is how they show up. So here we have some vehicles going on this through movement, and we have this blue vehicle coming down. Now what's going to happen is this blue vehicle is either going to turn here, make a left, or go through. Now here we see this blue vehicle coming up, and it's slowing way down because it needs to make a turn. And in order to make that movement, and with the animation recording, we can actually reverse it, so I can play it backwards. So what's happening is, even though this vehicle has the right of way on these two vehicles, right? So if I play it and I pause it right here and I go back into 2D mode and zoom in a little bit, this blue vehicle, if I turn on the conflict area, this blue vehicle has the right of way on these two vehicles. But there's a lot of complex issues at play here. So let me actually go back to the default network so you can see a little bit better. Now what's happening is this vehicle, even though it has the right of way, so this vehicle is technically going to yield to this blue car. This blue car needs to make a lane change. And since that blue car needs to make a lane change, it's not sure if this car is going to eventually decide to make a lane change itself and go through. So this car is actually seeing these cars approaching and then trying to make a lane change on its own. And it's not sure what this other blue car could do, because at any time this approaching vehicle can decide to go through, in which case this car now has to yield to this. So now you have this conflicting yielding behavior where they're both kind of yielding to each other because neither one really knows what the other one is going to do. So if I advance the simulation, you see the blue car slow down really slow until it sees that this car behind has committed to the lane, and then it can make a lane change and get out of the way. But you see, because of that, that vehicle had to make a really slow movement. When what you'd expect it to do is that both of these cars would stop and wait for this car to either decide to go that way or go that way, and then they would be able to proceed through. So these are the types of behaviors that you're looking for in the animation recording. So if you ever want to run an animation without having to watch the whole simulation, you could either have the consultant pre-record these, or you can just rerun it with an animation. So you can just come into the presentation menu, go to animation recordings, set up a recording like we did here for specific time intervals, and then you can record those animations. So you just select this record animations, run the simulation, see what the vehicles are doing. And this is something that you can record while you go to lunch or on a break, or you go home for the night, you hit play, go home for the night, come back the next morning, it's been recorded, and you can just play it back. So depending on how long it takes you to run a simulation, you can go, you can do that kind of in your off time, or not, while you're not, you don't have to sit and watch the simulation run. But yeah, so that's the kind of thing that you're gonna look for with regard to those animation files. Let's go back real quick and take a look at the turn value visualization um, for that cue. I want to find that cue again. I just want to real quick take a look at that animation and just see what's happening on this on that particular movement, right? So we're here. We see a lot happening, so I'm going to switch back over to the default view. And I'm probably going to actually turn off the links so we can kind of see what's going on without the links being on. I'm going to, actually, I'll do this. Sorry, just give me 1 second. Turn-based visualization, but I'll turn the links off and I'll turn off the node results. There we go. All right, so I'm going to hit play on my animation. I'm going to rerun it. And right when we start the animation, we can see, okay, we have a very long cue here with that's stretching all the way back, right? So in this case, I'm looking, and where was that left turn? It was right here. It actually doesn't look that bad for that left turn. They're actually feeding through okay. It seems to be more this area. Maybe there's a permissive left that is blocking a lot. So we see here a lot of vehicles trying to turn on their turn signals and things like that. So there seems to be some interesting behavior where maybe this dual left is being inputted into the wrong lane. That doesn't seem to be happening. Oh, there's no left turn there. It just seems that vehicles are just kind of stuck in that location. But we can kind of watch through and we can see what's going on as to why are these vehicles getting stuck. It seems to be a startup timing issue, vehicles making lane changes, things like that. So this might be a driver behavior issue, right? But this is where having this animation recording can really help you get some context onto some of those assumptions that we were making before. If you remember before, I was assuming that left turn far downstream was causing a huge queue spillback. It doesn't seem like that's happening. It seems like something right here is going on, where maybe the demand is really high, or maybe they've navigated everybody up to this turn, when in reality there might be more people coming this way. Because if you remember, nobody is going this way. So maybe some of this volume that would otherwise take a right turn and then a left and kind of go up and around, maybe it's all been by mistake navigated to this one right turn and it's blowing up this one intersection. So those are some of the things that you can consider investigating further with your animation recordings and things like that.